All right, today we're jumping into something really cool, a brand new way to build AI systems that are actually reliable and can scale up. It's all based on this brilliant dissertation that came out of Stanford. The big idea here is to stop treating AI like some kind of mysterious black box and start building it like real, solid software.
So here's how we're going to tackle this. First, we'll look at the big problem that's kind of holding AI back right now. Then we'll dive into this new programming paradigm that's designed to fix it. After that, we'll get practical and look at 3 specific tools that put these ideas into action. And finally, we'll wrap up by thinking about what this whole modular approach means for the future of AI engineering. Sound good? Let's go.
Okay, so first things first, let's talk about this weird paradox with today's AI. On one hand, it's just mind-blowingly powerful. But on the other, it can be surprisingly fragile, kind of unpredictable even.
And I bet you've seen this yourself, right? One minute, an AI is helping millions of people with super complex tasks, and the next, it's just making stuff up. Those hallucinations we hear so much about, or it makes a basic mistake in logic. It's that exact unreliability that's the real bottleneck.
So this research, it points to the root cause of the problem. And it's a big one. See, most AI models today are built as these huge, single, monolithic systems, one giant block. And that makes them a nightmare to control, to debug, or to improve just one little piece. The whole thing lacks what's been a golden rule in software engineering for decades: modularity.
Okay, so if that monolithic design is the problem, what's the fix? Well, this research lays out a completely new way to think about programming and engineering AI systems.
It's called foundation model programming. And honestly, the core idea is super powerful. It's all about shifting our thinking away from using one giant AI brain for everything and toward programming with smaller, specialized AI modules that we can piece together.
And I absolutely love this analogy because it just clicks. The old monolithic way, it's like a giant marble statue. Yeah, it's impressive, but if you spot a flaw, you pretty much have to resculpt the whole thing. It's just not flexible. But this new way, foundational model programming, is like a box of super advanced Legos. You just snap together the specialized bricks you need. And if one brick isn't working right, you just swap it out. It's flexible, it's iterative. That's the heart of all good software engineering. So, let's take a look at our first specialized Lego brick in this new toolkit. It's a system called ColBERT, and its job is to totally reinvent how AI searches for and retrieves information.
Okay, so the secret sauce here is something called late interaction. Now, the old way of doing search was painfully slow. A big AI had to read your query and then compare it to every single document one by one in real time. Just hugely inefficient. ColBERT is way smarter. It does all the heavy lifting beforehand. It takes all the documents and encodes them into what are called contextual embeddings, basically rich numerical fingerprints for the words. And it does this completely offline. So when you actually search for something, all it has to do is this super fast, really precise matching. It's a total game changer in terms of architecture, and it's what makes it so incredibly efficient.
And here's the proof in the pudding. Just look at these numbers. That architectural shift makes ColBERT over 170 times faster than the older BERT models. We're not talking about a small improvement here. This is the kind of leap that takes high-quality AI search from a lab experiment to something you can actually use in the real world.
All right, next up we have Baleen. And this system tackles an even harder problem. How do you answer those really complex questions where you have to find and connect pieces of information from a bunch of different places?
So, imagine trying to answer a question like, name an MVP of a game Red Flaherty umpired who was later elected to the Hall of Fame. Whoa, you can't just find that in one document, right? You have to connect the dots. It takes multiple steps, or what we call hops. So first, you'd have to find the list of games Red Flaherty umpired. Then you'd have to find the MVPs from those specific games. Then you'd have to cross-reference that list with the Hall of Fame inductees. See? It's this multi-step reasoning where most AI systems just fall flat. Baleen is designed to do exactly this. It automates that whole process. It does a search, finds a piece of the puzzle, summarizes what it learned, and then uses that summary to kick off the next, smarter search. It literally builds a logical path through all the data.
And the results are just wow. By creating this smarter step-by-step search path, Baleen massively improves the AI's ability to pull together information from all over the place. On a really tough benchmark for this kind of task, it took the accuracy from a baseline of just 15% all the way up to 57%. That is getting seriously close to human-level performance.
Okay, so that brings us to the final piece of this new paradigm, a tool called DSPy. Now, the best way to think about this is like a compiler, but for AI. Its whole job is to automatically figure out the best way to instruct our AI modules and make them work together.
I mean, we've all heard about prompt engineering, right? But the thing is, as this quote points out, handcrafting these super specific prompts is, well, it's brittle. It just doesn't scale. A prompt that works perfectly for one AI model might totally fail on another one, or even for the same model on a slightly different problem. It's kind of like trying to manually tune the individual connections in a neural network. It's just not a solid, repeatable way to build things.
And that's exactly where DSPy comes in. It basically automates that whole messy process. So instead of a developer writing some long, ridiculously specific prompt, they just define what they want the AI module to do using this clean, high-level thing called a signature. Then, the DSPy compiler takes over and figures out the how. It automatically finds the best possible instructions to give the AI to get that specific job done.
And again, the results are just stunning. Take a look at this. On a really hard set of math word problems, trying to do it with manual prompts was a struggle. You'd get somewhere between 9 and 25% accuracy. But a simple program compiled by DSPy, it skyrockets that accuracy to between 46 and 81%. That's a 3- to 4-fold improvement just by swapping out messy manual prompts for a clean, systematic compiled approach. It's huge.
Okay, so let's recap. We've got a module for super fast search, another one for smart multi-step reasoning, and a compiler to automatically glue them together in the best way possible. So, what happens when you combine all these ideas? What does this actually mean for the future of AI?
Well, the big takeaway is this. The future of AI isn't just a race to build bigger and bigger models. It's about being smarter. It's about designing better systems that use these models. By applying those timeless ideas from software engineering, like modularity, combining components, and optimizing the whole pipeline. That's how we get to AI that's genuinely reliable and can actually scale.
And that really leaves us with this final, really important thought. For a long time now, we've kind of treated powerful AI like it's this unpredictable magic. This new way of thinking, this foundation model programming, gives us the tools to finally move past that. It lets us build a next generation of AI, not on magic, but on deliberate, transparent, and solid engineering principles.